Oh, hello, hi, Kristin. I guess you cannot see.
Good morning.
Good morning.
Do you think we should start? What do you think? Is it time? It's exactly 5 o'clock. So I'm very pleased. My name is Stuart Parker, and I'm very pleased to chair the last talk of the workshop to be given by Kristin Persson from Berkeley. And well, she's done a lot of very exciting research. I looked at your recent publications. They look very interesting, particularly related, I guess, originally to the Materials Genome Project. And she's now director of the Molecular Foundry, which is a fantastic facility I visited several times in the past at the Lawrence Berkeley National Laboratory. And she's a professor at the University of California, Berkeley, and a faculty senior scientist at LBNL. And as I just mentioned, she was director and co-founder of the Materials Project, one of the most visible of the Materials Genome Initiative. And so we're very, very pleased that she's won many awards, and she's got a lot of very highly cited papers. And we're very, very pleased that she could join the workshop and give the last presentation this afternoon. Thank you very much.
Thank you. I hope you can hear me well. Does it sound okay on your side?
The sound is very good. Thank you.
Okay, great. Well, it's my pleasure to be here. I wish I could have attended in person. It's so much nicer to see people. I think we're all longing to get back to that mode of interacting in science, but for now, this is what we have. So I'll be talking about the kind of work that we have done to drive the era of data-driven materials innovation and design. So I don't know exactly where the audience is coming from. If you guys are chemists or physicists or material scientists, I sort of sit a little bit on each of those chairs in my work. But I am very excited about bringing our methodologies to our society to help bridge some of the problems we're seeing today. And it has been a bit of starting as a physicist, I have really embraced the mantra of material science, and I see materials everywhere in all of our technological advances and solutions. We wouldn't have our touch screens if we didn't have transparent conductors, highly sophisticated materials. We're using novel structural materials in transportation, in infrastructure, in health. And we certainly wouldn't be able to talk to each other like we do today and have our internet revolution if we didn't understand what defects do to light transmission in materials. So materials really do surround us and enable us. Unfortunately, materials development and design is not for the faint of heart. If you look at the materials innovation timeline, it has been shown through several studies that it takes a very long time from the time a material works in the lab. And that's when we publish and patent and kind of move on with our lives and think we're successful. So works in the lab to being commercially successful. It's on average 18 years. And there are examples of shorter timelines and even longer ones. But the consensus really is that materials are difficult to bring all the way from the bench to an application, because there are so many different properties that matter when you get to the end game, when you're actually trying to put it into a device and hoping that it works better than the state of the art of that device. So to give you an example, if we have materials that we, for example, a new photovoltaic, we tend to focus on the efficiency of the material, but maybe not how you can scale it up. What are the defect sensitivities in the materials during scale up? What's the cost? What's the temperature sensitivity? The halide perovskites is a great example because they're amazing efficiencies, but they do degrade during some of the moisture, for example, during exposure to moisture. So materials are just like a chain with links, and they're only as good as the weakest link in that chain. And we tend not to look at all the different links when we design a material. We tend to look at a few metrics of performance, and that's what we design towards. And if we don't do that holistic design, industry and society can spend decades trying to figure out how to fix those weak links and engineer around them, and that's what takes the long timeline. So that really brings me to what is the essence or the heart of my talk, that data is critical. If we had more data about materials, we would be able to make a better selection up front. We would be able to identify the links in that chain and say, you know, this material is so bad on so many metric points that we shouldn't really be looking at it anymore. We should be focusing on the materials that have more of the good properties, so we have a few of those weak links. The problem with that data in the materials world is that we don't have a lot of it available, especially not experimental data. Engineers spend hours finding property data to support analysis. We frequently duplicate existing data in the literature because we're not quite sure it was collected under the right circumstances. Frequently, we're dealing with outdated or inconsistent data, and we don't know who to trust. If you take just a simple, not so simple, but simple property like the elastic tensor, if you look in the literature, you find wildly differing measurements for the same material, or nominally the same material. And the source of data can take weeks to trace to really understand where it's coming from and how much we can trust it. So if you take, for example, let's say that I wanted to design a new thermoelectric material, what we typically do in our world is, in the academic world, is we focus on one or two metrics, and it's very often ZT. We try to find a material with higher ZTs, and that's important, of course. But if you then compare that to when you're going to implement a thermoelectric material into a device, and you look at the performance as a function of temperature cycling, time, degradation is one of the major issues in bringing that material to market, especially if you're now thinking that many of the high ZT materials are nanostructured materials, which can be very, very sensitive to exposure of temperature and interfacial reactions. So taking more of these different properties into account is kind of the part that I'm trying to highlight. Data is also the fuel of artificial intelligence, and we've gotten increasingly excited about using machine learning in different ways in our materials design endeavors. And I very often get this question by students, by investors, by others, like, why don't you use machine learning to solve your problems? And I said, well, the problem is the data, right? We have a lot of very cool machine learning algorithms, but they all need the fuel, the data, to run them. And that's the hard part. So if my students want to come and do machine learning, they have to spend a year or two first collecting data, because it doesn't really reside in one place, except for a few notable exceptions like the materials project. So I usually liken the sort of the machine learning algorithm is like the Ferrari that you all want to run, but unfortunately that will take some sort of fuel. So hopefully I've convinced you that data is important. A little bit of a sort of trajectory here. I started as a grad student in Sweden in 1996, and I spent a whole year on calculating from first principles, so using density functional theory, the vibrational phonon dispersion curves of tungsten. So one element, 1 year, one property. And the reason it took so long were really for two reasons. The algorithms to calculate this property were very new, and we were still sort of in the realm of we had different codes. I was parallelizing a plane wave code. I had to fit the pseudopotentials. And of course, my computing power was not nearly what we have today. So if we now fast forward to 2021, we have over 130,000 inorganic, way more than elements on the materials project, with millions of calculated associated properties. And the kind of analysis that you need to have in order to turn those properties that come out of the Schrödinger equation into engineering properties. So what I'm giving you down here are some examples of analyses, anywhere from Courbet diagrams, which tell you something about the sensitivity to moisture for materials, battery materials, redox flow batteries, and interfacial solid state reactions. So if we have this data, the idea behind the Materials Genome Initiative was that we were going to try to move from a Edisonian design of materials, which is baptized after Edison because he spent many years trying to figure out what the best filament for his light bulb would be by literally testing one carbon-based material after the other. And in the end, he wasn't actually able to find the best one, which was tungsten, that was discovered or identified by a Hungarian group a decade later. But using our ability now to calculate materials and to fill out those links in the chain, the properties that you're looking for by computations. I'm not saying we can compute every single relevant materials property to reach engineering or commercialization sort of likelihood, because there are many things we're still in the development of calculating, but we can help, and we can help remove spaces where there are so many problems that you really shouldn't be looking there. And that's an important piece of information as well. So giving basically a number of more highly likely candidates and structures and chemistry families to identify for our experimental colleagues so that they can look at them. And hopefully I'll highlight some of that in my talk as well. We have sort of implemented this in a number of different studies or different cases. The first time we did this, and would make me very excited, was in 2005. We were hired as consultant by a relatively famous battery company for primary batteries. And they were wondering if there was anything better out there than manganese dioxide for their alkaline battery cathode. And the first time we did this was to, do these calculations, try to calculate voltages, capacities, corrosion reactions, because you're dealing with a high pH electrolyte, and that's a really important metric in this case. What kind of materials would potentially beat manganese dioxide? Maybe not in cost, because that's almost impossible, but at least in performance. That project really sort of set me on my career, in the sense that I went to Berkeley shortly afterwards and started the materials project, because I was convinced that we could actually do this. We could design novel materials with the use of computations. Since then, there have been a number of cases, not just in my group or the people associated with the materials project, but from all over the world of doing this sort of, when you've identified a material from computations first, but it has later then been synthesized, shown, or tested to work as predicted. And I'm just mentioning a few here, everywhere from batteries to photocatalysts to thermoelectrics, piezoelectrics, and again, I'll go through some of these. So I'll be happy to say that this is the first time that I've been involved in something that has actually reached commercialization. Duracell in 2019 commercialized one of the materials that we gave them. We gave them a list of 200 after screening 10,000 materials that we thought had a higher chance of making it, that being better than manganese dioxide and being a viable way forward. And they basically explored almost all of them. And one of them really caught their attention, and they were able to, within 10 years, bring this to market from computation, so not really from the bench, to market in about 10 years. So the materials project was built around this vision that we can together, not just by computations, but together with our experimental colleagues, accelerate the materials design timeline. So what we do in the materials project, we're built around 4 pillars. We develop the code so that we can robustly calculate materials properties across different structures and chemistries, which normally takes a lot of finicky changing of input parameters, so that you're running your quantum chemistry or quantum materials code correctly. So we run those automatically on High Performance Computing Center, and we then collect automatically that data back to databases. We funnel that through an API to our website, as well as directly to the community. And in some cases, we use that data for our own design of novel materials, so that we can showcase, how do you use this data? What are ways to pick the different properties for different applications and turn that into a design vehicle for optimized materials? So I'll talk very briefly about these 4 pillars, and I'll give design examples. I think that's what most people are mostly excited about. So very briefly on the materials project codes and the data collection, because I do want to emphasize that this is one of the hardest parts. The fun part comes with the machine learning and the design of novel materials, but actually the hard part of collecting the data takes the most amount of time. So we have a number of codes that are all open source that we've developed within the materials project in-house. PyMatGen, which is our input and output code that basically turns the Schrodinger equation output into engineering properties. Fireworks, which is our dynamic workflow code that allows us to make decisions in real time. Imagine instead of your graduate student or your postdoc sitting and saying, that calculation didn't really converge, I need to change the input parameters. Our Fireworks workflow do those kinds of decisions on the fly based on previous experiences. And we combine PyMatGen and Fireworks into Atomate, into these recipe-based workflows that we have designed for a number of different properties. And then we use the API, which also is designed in-house, but I'm happy to say that I'm seeing a lot of collaboration across, especially with Europe, on coming up with common APIs that will allow our different databases to speak to each other. So when we started this endeavor, it was a fairly new endeavor. So we had to decide, and this is still, I think, contentious in our world, because we know that it takes a lot of time by students and postdocs and staff to develop these codes. But we made the decision early on to become open source, and we have never regretted it. So we get a lot more eyes, and we have collaborators and developers across the world that help us, especially with PyMatGen. We have the model of benevolent dictators, where these people are so committed that they spend their evenings and their weekends on looking at the code commits from other people and vet it before they're adopted into the master branch. So in some sense, this is why what we're doing is part software infrastructure development, part material science, and part actually talking to engineers. And so it sort of spans a lot of different disciplines. So the people that work in this space, I would say, are becoming highly interdisciplinary. We also recognize that if this is going to be something that lasts, you have to have very clear documentation. You have to avoid the kind of generational code rot that we see very often, that when somebody leaves a project, then the code they developed becomes very rapidly declines and becomes obsolete, and 2 years later somebody else have to recode the entire thing. We really want to avoid that. That is a tremendous waste of resources. So documentation and updates to the code are really, really important. So we try to do that, and we test. We test all the time, and the code breaks all the time. So this is a continuous fight against entropy. We have meetings every week to go through and to have code review. We also realize that data also gets updated and becomes obsolete. In the case of density functional theory, we are very happy as soon as there are improvements, both in terms of code, in convergence, in functionals, in accuracy, and we're constantly recomputing old data in the materials project. We're not just storing the data from like 2011 and assuming that that was state of the art back then. It's not state of the art anymore. So this also is a part of it. It's a living, breathing database. And that's why we also want to make sure that people understand that they have to cite the database version when they're using the data. So just to give you an example, if a student, in this case, I'm working with Mark Asta at UC Berkeley, and his student was working with my postdoc to benchmark the first workflow we had on the elastic tensor calculation. It took them basically a year to benchmark this to the point where you can just push a button and give it any metal, any insulator, any semiconductor material with a reasonable number of atoms per unit cell. And it will calculate the elastic tensor within plus minus 15% of the most accurate elastic tensor measurement that we could identify in the literature. And I want to highlight the fact that we are really dependent on those gold standard experimental data, because otherwise it's very hard for us to know that we're doing the right thing across chemistries, because there are knobs to turn in terms of convergence, in terms of K-point densities, and those different kinds of parameters that you can choose when you calculate the properties of materials. So they were able to do that against every single data. We had 200, not more than that, 200 full elastic tensor measurements that we believed were good enough to compare to, that we knew the structure. And after that, you sort of just hope that you've got it right. And you got those 200 right, then you go and you calculate. Now we have 13,000 calculated elastic tensor. It's by far the largest resource of elasticity freely available to the public in the world. So I'll give you a few examples of design. What we do is that we tend to go after a specific materials property or what has an application associated with it. And what we first have to do is then, of course, make sure we can calculate that property robustly. And then we figure out what kind of materials metrics and what kind of properties, including the sort of most important metric like efficiency, but what else do we care about? We might care about stability in a certain different environments. So I'm going to give you examples of a Magneto-Caloric discovery project, a piezoelectric materials discovery project, and a water photocatalyst discovery project. And in each case, I highlight what kind of material we identified and what the real bottleneck in terms of going from prediction to synthesis, validation, characterization was. And I think you'll see a theme that synthesis is becoming very rapidly something we care more and more about. It's very difficult to know if you're going to be able to make a material or not, depending on just the calculation of its properties. So starting with the Magneto-Caloric the design project, the first thing, of course, if you're going to design a magnetic material, I'm sorry, I'm in a very energy efficient building, and if I don't move enough, then then they think I'm not here and they shut down the lights. So I'll occasionally do this. So when you're going to design a material with magnetic properties, of course, you have to have a workflow that can robustly predict the accurate magnetic configuration of materials. So we started out with designing a workflow for collinear magnetic behavior, and that was published in 2019 and benchmarked against the best magnetic characterization data of oxides and other kinds of semiconducting materials that we could find. We're disseminating the data, and we are in the process of calculating all binary and ternary magnetic materials ground state, which is a large endeavor because you have to go through all the different iterations and at some point decide like, okay, I think I found the lowest energy. And we also use this data to test it to see if we can actually identify novel Magneto-Caloric materials. So Magneto-Caloric materials are materials that are being considered for things like consumer refrigeration, basically replacing the compressor technology, waste heat recovery, but there are only a few of these materials known and they're highly engineered. So it would be interesting, it would be good to have new beginning materials that you can then optimize further. The whole idea is that you're switching a material from a paramagnetic to a ferromagnetic state with the help of a field. And if that magnetic transformation couples to a structural transformation, you tend to get a large change in entropy, which is associated then with a change in heat. So you can basically absorb and desorb heat with the switching of your field and your material's magnetic and structural properties. So this was a property that excited a collaborator of mine, Ramses Chowdhury at UC Santa Barbara. He plotted the different materials that they were able to see today that had decent Magneto-Caloric response with something that he called the Deformation Descriptor, which is basically the volume change, the calculated volume change of a material between the non-magnetic and the ferromagnetic state, which is a reasonably easy thing for us to calculate. And he was able, using this descriptor, to identify some interesting materials, but we were also interested to see if we could partner with him and scan the whole materials project for possible high-performing, large entropy, so with high on this descriptor scale, materials in the materials part that hadn't been considered before. So we did that. We calculated this magnetic deformation parameter. And as you can see, there's, of course, most of your materials fall in the not so great performing bucket around basically zero magnetic deformation. But there is a tail, and that sort of tells you that there is some promise out there. There are materials that outside of the known ones that have a potential predicted high magnetic deformation. So we're looking basically up here in the 6 to 8%. One of these materials was a Manganese Antimonide, and this is a material that is known. It's known how to make it, but it had never been identified as a Magneto-Caloric material before. So that was new. But the good news is there was a synthesis recipe for this material. So as we calculated and thought that this one should be fairly promising, the Seshadri group went about to make the material and test it. And indeed, it is a magnetocaloric material. It had a high response. It's in its stoichiometric state, but it also incorporates non-stoichiometry. So you could put manganese interstitially in this material, which degrades actually the entropic switching, so less heat absorption, because you're now including an antiferromagnetically ordered manganese as compared to the ferromagnetically ordered ones on the original sites. But it also gives you a way of tuning the temperature, which is important. So it's a new member in the families of magnetocaloric materials. And I don't know if it's going to be technologically important, but at least, again, it's a new candidate. And it's interesting to see if people can optimize it further. So that's one example. And I want to highlight that this was the identification of a known material that we knew existed and had been made before. So we usually call these guys low-hanging fruit because they're known to be, they're known, we know how to make them largely. The next example I'm going to mention is less low-hanging fruit. So we were interested in finding novel piezoelectric materials for sensors, specifically focusing on if we can find things with high polarization, but not containing lead. Replacing PZT is a big deal. It's a $1 billion industry of sensors, very small amounts of lead. So it's not that bad from one sensor to the other, but they exist pretty much everywhere. And there's a large amounts of potential lead going into the waste stream from waste electronics. This is really something we want to replace. I believe PZT has got an exception in Europe from the sort of banning of lead generally in industry because of its technological importance. So we benchmarked again the workflow for piezoelectric tensor, and here the data was even more scarce. In the open literature, we only had 50 piezoelectric tensors measured to compare to before we decided that our workflow was good enough, because it was reproducing those piezoelectric tensors plus minus 20% in this case. We have now calculated over 3,000, and they're again available in the materials project. And we set about to design a novel piezoelectric based on that data. So in this case, we were again looking for a material with a high piezoelectric response that did not contain lead. And we had some very fearless collaborators at NREL, one of our national laboratories here in the US, that were interested in seeing if we could make a material that had never been made before. Their interest was not just in the piezoelectric part, but also in the synthesis aspect of the challenge. So we took a material that had never been made before, instead of taking one of the more low-hanging fruit, the materials that have been made. And this was a distorted perovskite, a strontium hafnium oxide. And I'll tell you why this was a very challenging project or material to go after. If you look for strontium hafnium oxide with that stoichiometry in the materials project, you'll find a table that looks something like this, where the green highlighted fields are the known materials or polymorphs in the space. So they have already been made. They've been shown, somebody has made them, and there are 4 of them. And the one we are trying to make, the one we wanted to make was this guy here. It's higher in enthalpy compared to the ground state. It's not the ground state. It has never been made before, and it's competing with 3 polymorphs that are lower in energy in the same stoichiometry. So this is really difficult. This means that you have to tailor and really tune your synthesis conditions to this particular polymorph. What the NREL team was interested in was saying, well, they were expert in epitaxial growth. So we were trying to see, could we tailor the substrate specifically to penalize those more lower energy polymorphs and promote this particular one? And we actually used computations to do that as well. We looked at the lattice mismatch of the more stable polymorphs versus the one we wanted to make with existing substrates. And we were able to see that one particular strontium titanate substrate that we doped with niobium would really sort of skew slightly the energetics such that our film should be more energetically favorable if we templated on this substrate. This was a challenge. It took 2 years. 2 years for the NREL team to go all the way from the prediction to making this substrate, this niobium doped strontium titanate substrate, and to tune the synthesis conditions such that they avoided the ground state and had the right and got the right tetragonal targets phase. And then we're able to characterize it very carefully at SLAC to make sure we had indeed made that film and not any of the other polymorphs that were reported to be more stable. So I really want to give a huge amount of credit to that team because that was a long road. But it turned out that this phase could be made with the right templating. If you grow it thicker, it actually transforms, so it is definitely metastable. But it was confirmed ferroelectric as well as piezoelectric with a fairly high breakdown strength in the thin film form. My last example, and now you're seeing the sort of, okay, the first Magneto-Caloric design example was about the material that was identified but already existed. The strontium hafnium oxide piezoelectric material is a material that had never been made before. It took 2 years to make and characterize. And now I'm going to give you an example of what happens when you combine the high throughput computations and design with high throughput synthesis and characterization. So this is a collaboration with John Gregoire, who is part of JCAP now. It's called LISA, the Liquid Solar Fuel Alliance, and with Jeff Neaton and me within the Materials Project. We were interested in identifying novel water splitting photocatalysts, especially on the oxygen evolution side of things. And to find a good photoanode, we need a couple of criteria that, so again, links in that chain, right? We need a valence band maximum that is close to the oxygen evolution potential. We need a band gap that can absorb the majority of visible light, so somewhere between 1 to 2 eV. And we need photochemical stability. In this case, we're going for alkaline because it's slightly easier than acid to find materials that are stable under high pH, because of course we're going to have to operate in water if we're doing water splitting. So this is a really important criteria, just as it was for our alkaline batteries. If you're going to operate within the media that is corrosive, you really need to screen for that property as well. So in those days, this is now a few years old, this project, we looked at the existing body of known photocatalysts for oxygen evolution. And there was the sort of semiconducting families that you see did pretty well on criteria number 1. So you see a lot of green yeses there. Sort of okay on criteria number 2, but really quite badly on criteria number 3. So yes, good electronic structure properties, but not so stable in the environment where you need the material to operate. It doesn't really matter how great of a band gap and how well your bands are aligned if your material is either going to decompose, form a passivating film on the surface, or dissolve in the environment that you're designing it for. So then we're looking towards the oxides, and the oxides are more stable under these conditions. So they do well on criteria, or okay on criteria number 3, but not so well on criteria number 1 and 2. So what we were interested in seeing, does the materials project, with all its data and its ability to calculate the electronic structure of materials, given its advantage of identifying specific oxides that really have those unique properties of the right band alignment and the right band gap for this application. And so we decided not to go after the whole project, all of its data, but focus on chromium, manganese, and vanadium-based ternary oxides. This was in discussion with our experimental colleagues who thought that this was a promising space to go after. If you just filtered in those days on oxides that contain chromium, manganese, and vanadium in the materials project, you get about 3,000. And this is a search you can do that will take you 5 minutes with our API. So no calculations have been made yet. You then sort or screen on phase stability and band gap, and you're using a particular functional for the band gap, so you need to be very generous. We tend to underestimate the band gap, so we're filtering between 0.2 EV and 3.5, even though we want to be between 1.1 to 2, because we know we're not very accurate on that metric when we calculate it. So we're taking a wide window of, sort of inclusive criteria here. And we're down to 400 of those materials that have potentially a good electronic structure for a good photocatalyst. Again, I haven't done a single calculation yet. This is all data that's available in the project. Now we're down to 400. In those days, that was sort of doable. That was acceptable to doing HAC calculation. HAC is another functional that tends to do a bit better on the band gap. So now we can We can tighten the criteria for the band gap to 1.2 to 3.2, and we're now down to 169 possible candidates. So now we calculate surface properties, so band edge energies, and we also screen on stability in water, criteria number 3. And we get the magic number of 47. 47 materials that we thought were reasonably good ideas for Jean Gregoire to try to synthesize and look at from his perspective in terms of photocatalytic activity of oxygen evolution. And these were the results. And this is the cool stuff again, when you don't have just one phase. We had 47. We gave 47 polymorphs that passed the computational criteria. 17 of them he was able to synthesize, which is quite remarkable in a fairly short amount of time. And 16 of those 17 exhibited a photocurrent. They're not all as good. You can see from this graph here that where the radius of the circle is a sign of how much photocurrent we're getting. So bigger circles, better. And that really did correlate. So even though 16 out of 17 had some response, some were better than others. And that really did correlate also with what kind of states we were able to see at the conduction band minimum and the valence band maximum. So having a high amount of vanadium 3D states at the conduction band maximum was a good thing, because then you're basically lowering to getting a better, tighter band gap, and having a low amount of oxygen 2p states with basically, which tend to correlate with low mobility. So you want to avoid those as much as possible at the valence band maximum. So those two design metrics now helped us to go forward and screen or look for more materials that were more promising as well. So I've given you 3 examples of successful materials design endeavors in 3 different categories. I also want to say that there are many times when we come up with great materials we think that we have never been able to make or have never been able to convince any of our experimental colleagues to go after. Here is a magnesium cathode that is a double substituted material. So it's based on existing structure, but no one has ever made this chemistry, and it has only been made when we have 2 other cations in the structure. So far, we haven't been able to find anyone who's willing to make it. But if it can be made, it is predicted to have amazing magnesium mobility. So I'll just tell you that there are a number of these guys out there too, that things we have predicted, but so far we don't know if they're real or they can be made. So this brings me to the science of synthesis, which I really do think is a frontier of computational material science, because we're seeing that we can compute all these amazing optimized materials, but we're waiting anywhere from months to years to maybe never to know if they can be realized or not. We need to get better at understanding, not just screening out and figuring out which classes to look at, but also on that, not on just on the property links in the chain, but also, can I make it? And if I can make it, what is the best possible ways to promote this material versus others, considering all the different ways we have of making novel materials? So my group is doing a fair amount of this, and I'll give one example of the things that the insights that we have garnered of looking at how can we bound synthesis space in one way or the other. If you look at some statistics out of the ICSD, so the ICSD contains the materials that have been made. The materials project that contains a lot of the ICSD structures and chemistries, but also our own hypothetical materials, things that we don't know if they can be made. And if you take just the statistics on the things that have been made, you can see that synthesizable materials really do correlate with energy above hull. So that which we can compute. We can calculate the energy of all the different competing polymorphs and see where are you in the metastability of things. How high are you above the basin of the lowest energy level structures and the decomposition energy towards those. So yes, energy above hull is a frequently used criteria for synthesizability, but it's not good enough. You can see that there are plenty of materials that can be made that are higher than about 100 MeV per atom. And this is just for oxides. If you're looking at the bar graph, when you break out different classes of materials, you see that oxides, yes, you hit about 80% of all synthesizable materials if you put your criteria at 100 MeV above the ground state. But if you go to nitrides, you only catch 50%. So the class of nitrides clearly have a much higher degree of tolerance towards metastability than oxides do. And if we just put it at one number, we're not going to be able to catch a lot of promising nitrides. So we need to do a little bit better in terms of screening what can be made and what cannot be made, more sensitive to the chemistry. So we started thinking about like, well, in synthesis of materials, what are you really competing with? Let's take an example. You want to make a particular tantalum nitride, and you're starting out from your precursors of tantalum oxide and ammonia. And you're wondering, can I make my particular target material, my particular polymorph, or am I just going to make amorphous junk? And what I would postulate is that you can always kinetically make the amorphous gunk, because you're already breaking bonds in the tantalum oxide and the ammonia. So just scrambling that together shouldn't be, you have to do that anyway. That's always possible. But what about thermodynamically? What does the thermodynamic competition between the crystalline states and the amorphous state look like? So if you illustrate, or you sketch the thermodynamic, the Gibbs free energy of different polymorphs, and you estimate the Gibbs free energy or the enthalpy of the amorphous state, we can calculate the enthalpy for the polymorphs pretty well. We can approximate an enthalpy for the amorphous state by scrambling the atoms in different boxes and making sure you get the right density, and then calculate different snapshots of different amorphous states and averaging that. That gives us at least an idea of the enthalpy of the amorphous state. What we can assume is true that the amorphous state, which is it's a highly increased disorder and is almost liquid-like structural state, frozen, should have a much larger entropy than any of the other ones. So as you go up in temperature, you can see that polymorph B and C, which started out with a lower enthalpy than the amorphous state, they have a window of thermodynamic stability compared to the amorphous state. But polymorph A, that starts out with a higher enthalpy than the amorphous state, never has a shot, because it's always going to be thermodynamically unfavorable compared to the amorphous state, which now is kinetically as well as thermodynamically accessible. So we're hypothesizing that an energy limit for polymorph synthesizability is set by the enthalpy of the analogous amorphous phase. So let's test that. And we did. Over 44 systems with different stoichiometries spanning oxides, nitrides, different elements, we calculated or approximated the amorphous energy, the enthalpy of the amorphous state. And we then put that on a graph, and we plotted the enthalpy of all the polymorphs in the materials project and the ICSD that have been made in under those stoichiometries, and as well as the ones that either have never been made or have been made at high pressure or some other conditions. And when you bring them down to room temperature and normal pressure, which is what we're doing the analysis under, they amorphosize or decompose. And we're seeing a remarkable agreement between the amorphous limit, the synthesizability limit, and what can be made or survives under our conditions. So all the filled circles are materials that have been made, have been synthesized, and survive under normal standard conditions. And all the empty circles are things that have never been made or have been made at some weird conditions. And once you actually release the pressure, they amorphosize. So we believe we have found at least a metric to screen out particularly bad ideas. As you can see, the energy scale here is pretty large, 200, 400, 600. So it's not tremendously sensitive in the energy scale, but it is much more sensitive. You look at the differences in terms of different kinds of chemistry of the compositional sensitivity. So let's take a few examples. If you look at boron oxide and boron nitride, boron oxide doesn't actually mind being amorphous as long as you're keeping the local little boron oxide tetrahedra. They can float around in different environments. So the amorphous limit for boron oxide is pretty low. It's only about a 50 MeV per atom. But boron nitride hates being amorphous. So that's where you have a much larger window of synthesizability of other polymorphs, because the amorphous limit is not so competitive. It's up at 600 MeV per atom, which is starting to tell you a little bit about why nitrides have such a high degree of metastability, because basically they hate being amorphous. So it's not a competitive state. And then of course, the skyscraper is your carbon system. The buckyball sits about half an EV above the ground state, and we can still make it because the amorphous state is again so penalized, it hates being amorphous. So that gives you a sense of what kind of classes can we look in for really exciting polymorphism, where we have large windows of metastability. And we're even sensitive to different kinds of like, say, a stoichiometry. So vanadium oxide, VO2 versus V2O5. So that can also give you a sort of a sense of where to go in terms of stability. And we call this a synthesizability skyline because it kind of looks like a skyline with all these different different amorphous limits. All right, so I think I'm getting to the end of my talk. So I'm just going to briefly mention the outreach and the data dissemination of the materials project. I've talked a lot about different materials that we've made. Here are some more that we've designed from first principles and then have been tested and validated. I want to show that because we give out so much data to the public, we can do associated machine learning, and the community can do its own machine learning as well, which I think is a tremendous leveraging of each other's properties and capabilities instead of redoing and recomputing, remeasuring the same data over and over again. We need to get better at sharing. So as an example, we have calculated 13,000 elastic tensors, but we're also using machine learning algorithms that if you come in and look for an elastic tensor in material what we haven't measured or calculated yet, you can click on a little link that says get predictions, and it gives you a machine learned prediction of the bulk modulus and the shear modulus. We do similarly on our calculated XFs and ZANEs, K-edge and L-edge, which we now have over 500,000 spectra on the materials project. You can upload your own spectra, and if you just know that, yes, this is some sample I made that contains aluminum and oxygen, we use machine learning algorithms to correlate the local environments in our crystalline spectra to your measured spectra and give you a ranked list of materials, crystalline materials, where we think the local environment looks as much similar as possible that you're collected. So again, hoping to accelerate the characterization of novel materials from a local descriptor of the structure. And we're seeing a tremendous excitement about the data that we deliver. So in 2020, you can see the bar graphs growing. We saw on average 1 paper per day citing the materials project for machine learning being published. And we want to highlight that people who use our data, such as here, 2 different groups, one that came up with new phosphor materials and one that came up with new super hard materials. Again, using our data and actually doing machine learning on it, filtering, coming up with their own stuff, and then publishing new materials that have never been seen before with specific properties using that data. We have over 200,000 registered users on the materials project today, and we're seeing a large growth. It keeps growing exponentially. We have to now spin up our servers on many different servers depending on the demand. And we deliver somewhere between 2 to 45 million data points per day through our API. And we're used all over the world. And we're very excited about the collaborations that we're seeing and the community. And with that, I'll just thank my group, my sponsors, and I'll be very happy to take questions.
So now we have time for questions and comments. So would anybody like to ask a question? Maybe I could start off with a question. I just wondered how you deal with phase transitions. Because, for example, you mentioned tungsten oxide. That's a super interesting material, tungsten 03. If you dope it with potassium, it becomes superconducting, or you put in a tiny numbers of vacancies, that you can change the conductivity by 8 orders of magnitude. I just wondered to what extent, or let's say vanadium, you mentioned so many oxides, vanadium oxide, famous for its metal insulator transition. Is that something that you can deal with in your, with all the calculations that you've discussed?
So we can certainly calculate different polymorphs as I described. We can also calculate dopant to some degree. Within an approximation, we can dope the different sites, and we can figure out if that changes significantly the properties that you're looking at. Electronic conductivity is not one of the properties we're best at calculating. We could probably get you a proxy or at least trends within a family. The phase transformation in itself, like how that happens through nucleation and growth, or if it's some more of diffusion-less phase transformation, is more of an involved calculation. Then that's an investigation, not what I would call something you can calculate 100 different phase transformations or 1,000 different ones. But you can certainly change the polymorphs, change the doping level, change the composition, and seeing what the competition in phase space and structural phase space looks like, and then sort of see if you're likely to get a phase transformation or not, exactly how it happens.
So largely speaking, it's mostly to do more with the structure that you would be calculating and simple properties.
But and the structure and the chemistry would give you different properties, and then you can calculate those.
Okay, interesting. Because I just wondered, it seemed as though you were suggesting maybe no longer would one need intuition, that everything could be done using computing systems, and we could displace all those chemists and physicists and just have one big computer. What do you think?
No, I'm not saying that. I think intuition is tremendously valuable, and that's why we like very much. I work with experimentalists in almost every single one of my design projects, because I also realize that I can't be the expert in every single application that I'm looking at. So I want to hear from them before I go off and calculate anything. But I do think that computers can be really useful in telling us whether that intuition or experience is true, or if it's actually a bias compared to what we've learned previously. So if you think about Edison, for example, he was completely convinced that his filament had to be found in the carbon family. So he only went after carbon-based materials. And he was limited by time. And in the end, yeah, we found the best carbon-based, but it wasn't the best material. We have found some real surprises when we've gone and cast our nets a bit wider than people would have expected it. We found battery materials that we would never have expected to exist, because we are prejudiced to some degree by, yes, it's going to be these kinds of oxides, these kinds of layered materials, these kinds of spinels. If we look outside of that, is it possible to have materials that will have particular properties that are outside of our known sphere? So I think both are good.
But let's say you talked a lot about perovskites, and then of course very closely related Brown-Millerite phases, or all these planar oxygen vacancies. Is that something you can deal with? It seems almost impossible, because there's such a very interesting complexity of phases. How would you, you deal with that? Or
you can actually. So we have a paper where we worked with some German collaborators on perovskite and Brown-Millerite for solar looping, basically like phase transformation to store heat from CSP. And it's doable, but it is, like you say, a combinatorial explosion of where do the vacancies sit, and you know, so you have to approximate to some degree. Like you have to use smaller unit cells. You do a number of different configurations, and maybe you fit a cluster expansion or some simple model for what seems to be the low-lying states here. So you get an idea of what the energy landscape looks like and how that's going to impact your change in enthalpy as a function of the phase transformation. So it's doable, but yeah.
The comment you just made about the size of the unit cell that was mentioned yesterday by, I think, the last speaker, that let's say if you want to twist these 2D materials, well, you can't look at small twist angles where maybe that's all the exciting science because the unit cell's too big. So how big a unit cell can you calculate? Do you have some special techniques that could you calculate, let's say, twisted bilayer graphene, or is that something you could deal with in your computing systems? Could I ask?
Yeah, so we routinely deal with up to 300 atoms per unit cell. That's something we just put in the queue without thinking. But if we can go up to things like 1,000 atoms, probably, if we do more of specifically tailored calculations. Above that, there are ways of approximating DFT for even higher, bigger unit cells, but then you are talking about specific codes that deal with that. And so that we haven't gone. So I would say 300 to 1,000. 1,000 if you're pushing us.
Yes, well, I mean, I think it's super interesting, these, of course, these 2D, I mean, quite frankly, my interest is in interfaces. And I think you can deal with bulk materials, but interfaces by themselves even determine the structure, where the atoms sit, distortions, out of plane, and then the properties are amazing. So do you think there's a chance that your methods could be used to explore interfaces of distinct materials, let's say in oxides. One of the most famous cases, of course, is strontium titanate lanthanum aluminum oxide, which is a two-dimensional electron gas. And so, of course, physicists like two-dimensional electron gases. Can you make predictions about which of the systems might display 2D, let's say, given the thousands of papers on that particular interface in the last 15 years, and it's still not clear what is the origin? Could you help to resolve that issue?
Oh, so I don't know the system specifically, but I'll speak generally to interfaces. The question is, of course, is the interface stable? Does it react? Is there a very small amount of a passivating layer formed at the interface? Which is something that, from a thermodynamic point of view, yes, we can predict how two solid states, materials that are in contact with each other, should react if given enough time. So basically, if kinetically viable at some point. We use it very often when we look at solid state batteries, for example, because there we have highly reactive interfaces, lithium metal in contact with sulfides, for example. So you're obviously going to start making lithium sulfide on the interface. Is that going to affect your properties of your interface? That's when you have to start thinking. So the question is really, can we calculate the properties of a completely clean interface? Yes, most likely, depending on, again, what property you're looking for. But if you have any kind of reactivity at that interface, and any kind, right, then what we're calculating as the clean interface is not going to give you the right answer, because that's not what you're measuring. You're measuring something where you have two phases and then something else very thin in between. So the first thing I would really recommend is figuring out, what do you have? What kind of structure and chemistry do you have at that interface? Does that make sense?
Yes, that makes sense. And I think that's exactly right. You can get interchange of the atoms. You can get all sorts of very interesting distortions of the interface, lead to interesting properties. So I don't want to monopolize the time. So we should ask. The hand. Oh. Okay, Elena, why don't you ask your question?
Oh, yeah, I'll ask. Thank you first for the talk. It's very interesting, and thanks for material projects, because I've been using it a lot over my PhD. So thanks. And the question is, like, you've shown very nice examples of material design, and have you ever considered to play the same game with high temperature superconductors and kind of do this, over material projects? I don't know. Yeah.
That is a great question. So I haven't followed the field tremendously in the last 5-6 years. Have they come further in terms of understanding where it comes from? I was looking at there was sort of these ideas of magnetic phase transformation that was driving the high T superconductors. Because what we really need is an understanding of the underlying mechanism before we can go and screen for them. We can do the low temperature ones because we understand the electron phonon interaction, and we can calculate that. But I think the high T cuprates and so forth is sort of a combination of phase transformations and magnetic states. So
Yeah,
maybe you can help me out.
Yeah, okay. So you need theory.
So that's the problem.
You need theory for that, right? So, okay.
We do, yes, we do need theory for that. So we need people to figure out what should we compute before we can go and look for them, right? Because otherwise we're a bit in the dark.
Yeah, okay.
Okay, thank you, Elena. Now there's a question from Jin Liang.
Yes. So Kristin, thank you. Very, very, very excellent talk. So my question is more going to your very interesting point about the synthetic synthetibility of the amorphous image. So, I mean, because I'm a synthetic chemist, so I'm really intrigued by this work. So my question is, how do you consider during the calculation regarding the intermediate, how the intermediate is transformed to the final product, at which step or which key factors do you need to consider that the amorphous versus crystalline phase formation? And I don't know how much, maybe I skip the example, what exactly the reaction is involved in this particular case, because my next question relevant is going to more complex chemistry, especially when you're talking about the more complex inorganic chemistry or organic reactions, and how do you deal? How can you predict, such complex systems involving multi-step intermediate formation, and how can you predict that they can lead to the amorphous or crystalline materials? So can you give a comment on this?
Sure, absolutely. So just to clarify, when we do the amorphous limit, we're not actually calculating the transformation from your precursors into that. We're just doing the thermodynamic analysis whether the amorphous state is going to be competitive. thermodynamically, because we're assuming that kinetically it's always accessible. It should be, right? You're breaking bonds, you can always make gunk, right? That shouldn't be that hard. So if it's both kinetically accessible and thermodynamically favorable, we go like, there's no way you're going to make this polymorph. It's higher in energy, and it's competing with a kinetically accessible lower thermodynamic state. So that's number one. Number two, yes, we are working with experimental colleagues to try to figure out the actual pathway of synthesis, as well as just ruling out phases based on their energetics, which is what the skyline is about. So what we have been able to do, and we're particularly focused on metathesis, because that's a really useful way to promote certain phases. And we are again using thermodynamic data largely, because that's what we're best at. Kinetics is very, very difficult. But we can track the trajectories starting from your precursors in thermodynamic space, and where are the sort of attractors in terms of thermodynamics. Let's say you want to make a ternary or a quaternary. What we often find is that you're burning most of your thermodynamic driving force in making the binaries on the way towards that ternary and quaternary. And trying to avoid those sinks, those attractors that you're not trying to make, is a way that we can design the pathway. So if we're starting from precursors that have more of a, that avoids things you don't want to make, that are low in energy, that tends to sort of attract you, and then you're sort of, it takes months to make that actual ternary because you have very little driving force left. That's one way. We've also found that using a metric that we've come up with that we call the distance in chemical potential has been very, very helpful. So we have been, if you calculate the distance, the minimal distance in chemical potential between your precursors and your target phase, and that is very small, that tends to promote good selectivity for your target compound. And there are a couple of reasons for this. That means A, in thermodynamic space, you avoid other attractors, other phases that wants to form. And secondly, you have a good overlap in the chemical potentials between your precursor and your target. Let's take an example. You're trying to make a material and you're flowing oxygen gas, and you're assuming that that oxygen gas can get to your reactive site, right? Because that's what we do. We control the chemical potential of the oxygen. What we have found is that that's not very true. So if we take precursors with the right oxygen chemical potentials, you don't have to get the oxygen to your reactive site. So you have a low minimal distance in chemical potential distance between your precursor and your target. That gives you a better chance of making your materials. And that is a kinetic limitation, but we're using thermodynamics to get around it. So
great, thanks.
Fascinating. So I think, well, we have one more question, which I'll just read from Elena again. And she says, are you planning to add Fermi surface generation into the materials project?
Oh, that's a great question. We could do that. We have the data. We just haven't. Every single property that we add to the materials project requires somebody to take ownership of it to make sure that we're using the right parameters for the electronic structure calculation and the statics to get to the right one and then disseminate it. So we could do it. It's just we're limited. I have 4 staff that are permanent. That's it.
There are many, many more questions, and we really enjoyed your talk very much to give
my pleasure
knowledge and information, and we look forward to your further explosion of data on the materials project database. So we want to thank you, and we'd also like to thank the other 2 speakers, Professor Cariotti and Professor Vodek. Everybody has very difficult names to pronounce today. I think that's a common feature of the 3 speakers. But anyway, we want to thank all 3 of you and the 4 speakers yesterday for a very exciting workshop. We thank everybody for contributing and giving such interesting talks. And we hope in the future that we can perhaps even collaborate with some of you, because we're certainly very excited by creating materials that could have impact to solve some of the problems that some of you have pointed to. And thank you very much.
Thank you. Have a good evening.